When we want to model gas behavior, we almost always use the ideal gas law. The ideal gas law's most common form should be written as PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, R is the gas constant, and T is the temperature. And the ideal gas law was developed from several other gas laws that looked at the behavior of gases as we just changed one property at a time. Typically, they were studying two properties. So they would, for example, increase the temperature and hold the number of moles in the volume constant, and then look at the increase in pressure as you raise the temperature. So even though the ideal gas law is an approximation, the trends that we find from the ideal gas law, where if temperature increases, then pressure increases. If the temperature increases and we we hold the pressure constant, then the volume will increase. If we increase the pressure, then the volume has to go down if we're holding the temperature constant, and vice versa. That all of these trends, they are consistent. So they still work for all gases. They may not be exactly the same relationship that we get with PV equals nRT with the ideal gas law, but the trend is still good. And so this the ideal gas law is useful for us, especially if we don't mind making a few approximations. So one thing for us to remember is that there are a number of assumptions that are behind the ideal gas law. And the first one is that all of our collisions are elastic, which means that no energy is lost. The second one is that the particles have mass, but no volume. They don't take up any space. And sort of as a corollary to this, our particles are all spherical, and they are these little hard spheres that are identical. So you can calculate the pressure, the volume, the number of moles, or the temperature as long as you have the other three variables in the ideal gas law. The gas constant R is available with a wide range of different units, and I often have people ask me, which gas constant should I use? And my answer is the same. Use one that has units that are convenient to you. Wikipedia, for example, has a giant table of collected R values, mostly from the Chemistry and Physics Handbook, CRC, with a bunch of different R values with different units, so just look it up and pick one. So let's go ahead and work out an example problem. So a problem might say something like 25 grams of carbon dioxide gas were produced in some kind of a combustion reaction and then captured in a 1 liter container and it's combustion reaction, so things are pretty hot. So let's say it is at 50 degrees Celsius. And the question is, what is the pressure of the carbon dioxide inside that 1 liter container? So if we look at our ideal gas law, PV equals nRT, we can identify that the unknown is the pressure. So we need to solve for it. So we'll rearrange the ideal gas law to look like nRT over V. So some of these things we already have. For example, the volume we have is 1 liter. But the other numbers we need to do some conversions. So one thing that we need to remember is that our temperature must be in Kelvin. So we have 50 degrees Celsius. We know that adding 273.15 will get us to Kelvin. So if we add those together, we get 323.15 Kelvin. And when we think about our significant digits, we are using the addition rules here. And so that the addition rules, we look at the number of decimal places in our two different numbers. So our first number over here has 1 decimal place, and our second number has 2 decimal places, which means that our final answer really should keep 1 decimal place. So when we report our temperature, I'm going to actually do something slightly different than what we have been doing in Gen Chem, which is I'm going to write my number with a subscript, with the 5. And in quantitative analysis, this subscript 5 means that this is my first uncertain digit. And I'm including it here because it might have some significance, especially because the 273.15 is part of a conversion factor. And so I'm going to go ahead and include it in here just in case it ends up becoming important later on. And in quantitative analysis, this is a not uncommon kind of thing to see. All right, so we converted our temperature. We also need the number of moles. So we are given that we have 25 grams of carbon dioxide, and that means that we need to convert this into moles. We know that we can do this using our molecular weight. So if we go over to our periodic table, we can add up the atomic weight of the carbon and 2 oxygens, and we will get 44.01 grams of carbon dioxide, which should get us 0.568 grams of carbon dioxide. And we're keeping 3 significant digits because we're doing multiplication division rules here, which looks at our 2 numbers and uses the smallest number of significant digits for our final answer as we had to begin with. So we have 3 significant digits in our carbon dioxide, and we could have had more than 4, just depending on where we found our molecular weights. So we need to remember that this 0 here is just a placeholder. It is not considered part of our significant digit count. And so this 0.568, these are our 3 significant digits that we are going to keep. So if we now plug our numbers in to our equation, we have 0.568 grams, moles of carbon dioxide. Our gas constant, we didn't specify what the pressure unit would be, so I'm just going to use the one I always use, which is 0.083145 liter bar over mole Kelvin. This one is handy because the liters will cancel out with my volume of liters, but it's not the only one that has liters, so you can choose a different one if you prefer. And if I don't specify what the volume, or excuse me, what the pressure units are, then pick whichever one you prefer. So if I look at my units, my liters will cancel out, my moles will cancel out, my Kelvin will cancel out, and my final unit here will be bar, which is a pressure unit, which is perfect. So my final answer, if I calculate this through, is 15.2 bar. And once again, with our significant digits, we had 3 significant digits in the moles, 3 in the volume, and 4 over here in the temperature. Conversion factors are, right now, we had 5 in this particular conversion factor, but most conversion factors you can find as many numbers as you want, so don't let the conversion, or excuse me, don't let the constant, like the gas constant or any kind of, Planck's constant, any kind of number you happen to be using, speed of light, don't let that limit your number of significant digits. You can always find the next digit there. Long story short, though, we're going to be keeping 3 significant digits for our answer, which is what we did. So we successfully did some unit conversions and calculated the pressure for ideal gas law.